Hello, hello. Good morning, good evening, good night. It is me, your physics influencer, dropping fresh new content to you. This is video 3 of circular motion. We are going to talk about vertical circles. How did this guy run the loop? Well, we will find out all about the forces that acts on this human being. And without further ado, I shall invite Miss Ellie to give you some demonstration.
Now I'm going to use one of my favorite toys, a yo-yo, to do a throw around the world. Here's how it looks like. Look at that, the string turned and the yo-yo is traveling in a nice circle. Now if the string breaks at any point, the yo-yo will definitely fly away. Don't want to travel in a circle. But my question for you is this. At which point is the tension the greatest? At which point is the tension the least? See the string? Different tension, you know. But where is greatest, where is least?
Alright, I'm back. So here, as usual, I'm going to walk you through some basic graphical analysis. So I'm going to visualize Miss Ellie's yo-yo, okay, and draw out a circular part and picture the yo-yo at different position along the circle, namely position A, B, C, and D. Okay, we are just going to assume that the yo-yo rotates counterclockwise. So step 1, label the forces, remember? Because we need to find the net force. So of course, the first force I'm going to label is weight, mg. Now that I look at this diagram, it looks strangely like a wind chime. Never mind. So there's mg going down. As you are probably used to me by now, I'm very off tangent. Okay, so mg. And then because obviously a yo-yo has a string, so there's tension as well. And I will label that after labeling the positions. So there will be a string here and here and here. Okay, so I'm just going to label off all the strings and label tension in it as well. Okay, right. So tension. So just a reminder for you, tension will always point in a pulling direction. And if you notice the way I draw the green arrow, let's say I label a tension at different position, they are of different lengths. And this is for a reason, okay? Because if you have played any yo-yo before, the tension is the highest at the bottom. If you have not tried this thing, okay? So anyway, at position 1, here I will prove and discuss how the tension will be different. So at position 1, we always do the same thing. We find net force. So here, net force will be equal to T1 minus mg because we are taking the direction towards the center as positive. Okay, so no longer up, down, towards the center is positive. So T1 minus mg is Fc. So T1 will be Fc plus mg. Because at the bottom side, the tension need to do two things. Provide centripetal force and support the weight. Very tired, that's why tension very big. At position 2, just the tension will provide the centripetal force because both 2 and 4, the weight component is 90 degree, so it doesn't interfere. Okay, whereas position 3, you will notice that T3 and mg is pointed towards the circle, so they are both positive, and you get T3 is equal to Fc minus mg. So the tension is the lowest at the highest position because it needs to do the least work. You have the weight to help it provide centripetal force. It can relax a bit. Okay, so that's why the tension at the bottom is the lowest. The bottom is the highest because tension needs to provide centripetal force and support weight. At the highest position, tension can chill a bit, T3, because weight will help provide centripetal force. Okay, so here I have included another drawing at some random angle theta. Okay, I'm just labeling the linear speed, random angle theta from the vertical. Okay, so and at this random angle, right, and this part is, I think it's only relevant if you do further maths, like the derivation, but you kind of like need to have a sense of how the tension changes over time because you can be asked to describe the variation of tension of the yo-yo. Then like that very susah, right? So might as well you just see the derivation so you can feel it lah. So anywho, at this point, you can find that our tension at the angle of theta, this tension needs to be resolved. Like all of us, the tension and the conflict in our life, it needs to be resolved. Okay, and you notice that I resolve this slightly differently than the conical pendulum because the center of the circle is at a different place. So I resolve a component that is parallel to the center of the circle, and this will be t cos theta, and another component that is perpendicular to the center, which will be t sine theta, which is not really that important. Always take the direction towards the center of the circle as positive. All forces that are parallel to this, we take. All forces that are perpendicular to this, we don't take. That's why we resolve. Life is good like that. Okay, so we can find net force towards the direction of the circle at position 5. Again, sigma F is MA. By the way, sorry, it's mg cos theta because you're resolving mg, not t. Whoops. All right, so t minus mg cos theta will be sigma F. That's the net force. Again, t is directed towards the center. That's why t is positive. So net force will be equal to centripetal force. And your your tension will be Fc plus mg cos theta. Like any good science student, you should know how to plot a cost graph lah. Okay? So, to think about this cost graph, you can see that it is a cost graph that is elevated because you plus Fc ma, right? So, there will be a bottom minimum, which is Fc, because your tension will change over time, right? So, you are trying to plot a graph of tension against mg cos theta. The smallest value that mg cos theta can take is 0. That is where your tension equal to centripetal force, aka position 2 and 4. Okay, so now I'm just going to wait for the pass me to finish drawing. Okay, so there will be a maximum and then there will be a minimum force. Okay, and then you will notice that the maximum and minimum points, right? Now think a bit about how you are going to draw the graph, especially if you come from a maths background. Maths background. Okay, so in the center position will always be there because we're trying to draw a cosine curve, an elevated cosine curve. Okay, so I'm going to zoom in here for you to see. As usual, the printouts will be there lah. So the center one is Fc. This is Fc plus mg. This is Fc minus mg. Okay? So it's elevated. Because sometimes it can be negative ma, your mg cos theta. So you can't get a graph that is like this. At certain positions, t would be Fc minus mg, namely position 3. And then at certain positions, t would be Fc plus mg. Okay, so it's a cosine graph that is elevated, but elevated because cosine graph got positive, negative ma. Elevated until it's entirely positive. Can the tension be 0? Very good question. Can. If you slow down the spin of the yo-yo, you will reach a point where the string becomes slack and then the yo-yo will not be able to keep a circular path. That is when you translate the entire graph downwards. But I think the main idea here that you should take away is there are certain positions where the tension is maximum, that is position 1, and then there's a certain position where the tension is minimum, that will be position 3. So if they ask you, the string will break. Where will the string break? Position 1. Where will the string have minimum tension? Position 3. So if you want minimum speed, you equate the tension to 0 because that means that any slower, the yo-yo cannot go up already.
Okay, so now it's a container of noodles. You see, noodles, right? If you turn upside down, it's all gonna crash and it's gonna spoil, which is not good because you know your family member's gonna scold you. So I'm gonna swing the container of noodles now. Okay, let me get there, and you want to give it a nice swing. So let's see. All right, let's slow it down a bit too fast. Okay, now slow can. Nice. All right. I want you to pay attention to the top. When the container moves to the top, look how the noodles is sticking on the top. It does not fall down. Why is that? What are the forces acting on the noodles that keeps it moving in a circle? Okay, so if halfway I let go, of course the noodle container will fly away lah. But yes, that's the first question. What keeps the noodle at the top of the container?
All right, so here is a drawing of the noodles. Okay, I'm just going to draw a yellow highlight to represent the noodles. The noodles. So Miss Ellie asked us about what is the forces acting on the noodles. Okay, so if you're going to think about forces acting on the noodles are in contact with the bottom of the container. Contact force. Okay, so first order of business, I'm a label the mg. The mg is always there. Gravity. Okay, so there will be some form of gravity, and then uh, we'll draw the normal force. So as I slowly draw, I want you to observe the similarities between this force diagram and the force diagram on your left, the one with tension. Are they strangely the same? Like horizontal circle, most of the force diagram looks very similar. Just like this one, the force diagram looks similar. It's just that the name or the type of forces will change. That's all. Okay? So at the highest position, right, if you need the normal force to help you provide centripetal force, the noodle has to press up against the bottom of the container because that helps you give you centripetal force. This is a lot like the washing machine, the front-loaded washing machine. When the washing machine is turning slowly, the weight of the clothing will pull the clothing down. The clothing will go up the circle and then fall down, go up, then fall down. But if the washing machine is spinning fast enough, then the clothing can go in a complete circle. So you need it to go fast enough. So as you can see, since the force diagram is identical, I can infer that the equations will all be the same. You replace T with normal contact force N, like that. Then everything is the same. Maximum at the same places, minimum at the same places. Equation will look the same. Replace the T's with N. Yeah, that's all. Okay, we'll do a question soon. But that's the idea lah. So if they ask you if the rope snaps or whatever, then this one means T is the greatest, is the at position 1. Or where the noodles break, then greatest is position 1 lah. If the noodle drops from in the container, then your normal is the smallest, and the smallest possible value of normal is 0, my favorite number. Okay, the noodle will then loses contact, and mg will be equal to, okay, and mg will be then equal to your net force. So in other words, right, you can think about it like a form of weightlessness. Okay, when I say weightlessness, I mean at this position, if you instead of the weight pulling you down, instead of this weight pulling you down, what you are experiencing is actually the weight providing you centripetal force necessary to move in a circle. Okay, so if let's say I hang a spring here, the extension of the spring here would be the smallest. Sorry, if I hang a spring up here, the extension of the spring up here would be the smallest because the tension up here is the smallest. Does that make sense? Okay, so it's the same thing here. Okay, if let's say you want to talk about the forces acting on the noodle, which is the weight of the noodle and the normal contact force, the smallest possible value of N is 0. Once the noodle lose contact with the bottom, it will fall down. Okay, meaning you are not turning fast enough. Turn faster. When you turn faster, look at the equation at position 3 here. This is noodle, right? N for normal, N for noodle. So when you turn faster, you will need more centripetal force. Meaning this number will be bigger than 0. Meaning the noodle have to press against the bottom of the container. Okay, so the larger the centripetal force, the higher you will uplift your cosine graph. Make sense? Okay, so right now we are going to look at a different example, but again pretty similar. You have a pilot at both top and bottom position, And it is at this point that you will notice that you can see the diagram is so similar. At the bottom position, you have a large normal force. At the top position, you have a small normal force. It's the same thing. This is because at the bottom position, normal force have to support weight and provide FC. At the top position, it doesn't need to. But you notice that the top position, there are two different variations. If the plane is inverted, and then the other one is when the plane is upright. Very different, huh? Because when the plane is upright, the normal force will act upwards. If the plane is inverted, the normal force will act downwards. This is because it depends on where you sit lah. The normal force must be always acting away from the contact area, the contact surface ma. Okay? So in either way, if this is the case, right, you will feel lighter for the first one. If this is the case, you will feel heavier. We can do a question. Basically, just draw the forces and then infer from there. Okay? So we are going to continue and do an example. All right? So this is related to the noodle, but instead of a noodle, now we are going to have a bucket of water. Bucket is swung in a vertical circle of radius 1.2 meter. What must be the minimum speed of the bucket at the highest point of the circle if the water is to stay in the bucket throughout the motion? Well, for this one, what we will do is we will try to draw the bucket at the highest position. Normally, the free body diagram will help. Bucket is optional, but drawing the forces is not. Okay, so obviously you have the weight of the water, mg, going downwards. Okay, and there's also contact force, N. So at minimum speed, N is 0. Ooh, forgotten to turn on the camera. Minimum speed, N is 0. All right. And so you can say net force will be mg plus N. Again, center of the circle is positive. So centripetal force is mv square over r is mg plus N. Equate N to 0. And you will get v square is square root of r. V is square root of rg. So once again, you will notice that the minimum speed is not dependent on how much water you put in the container. It just depends on the radius of the circle. Okay, the bigger the circle, the faster you have to run. Okay, or faster you have to turn. The stun diagram I showed you in the beginning will be linked in the description below. There's a cool video that you can watch. All right, next question. In an air show, an aircraft diving at a speed of 170 meters per second pulls out the dive by moving in the arc of a circle at the bottom of the dive. Calculate the minimum radius of the circle if the centripetal acceleration is not to exceed 5 times the acceleration of free fall. So 5 times g is your maximum value. So in this question, once again, draw forces law. I do this kind of question so many years. I will still draw forces. It's just a very good thing to have to help you organize your brain, your ideas. So again, I'm just going to take the forces acting on the human. I'm assuming the human is strapped to the ground, so there's some normal force pointing upward. So N minus mg will be equal to MAC. Okay, just to get that out of the way first. Resultant force provides centripetal force. But since they are looking for centripetal acceleration, I'm a little teensy bit cannot continue here because I do not know at that point the mass of the human. Neither do I know the normal force. Okay, so never mind. I will just use AC is equal to V square over R. So you then will get R is equal to V square over 5G. And then you can substitute lor. mv square over r can be used for any circles as long as the particle is traveling at constant speed. Not constant speed means have to use calculus now. Alright, anyway, substituting all of this in, you will get that the radius have to be a pretty hefty 589 meters. Next, what's the resultant force? So resultant force is ma ma. You already know the acceleration, the upward acceleration, which is the centripetal acceleration, which is 5g. So you just take m times 5g. That's all. Okay. So extra, bonus, find N, the normal force acting on the pilot at the bottom of the circle. Okay, so if you want to be able to find N, you already have the resultant force, right? So Fc will be equal to MAC, which is the resultant force, but Fc is also equal to N minus mg. Once again, direction of the center of circle is positive. Substituting the values in, you will notice that N is equal to 6 mg. So this 6 mg, right, actually shows you that, hey, the the pilot is actually experiencing a lot of G force. 6G can actually knock you unconscious because your system cannot handle very large acceleration. So when the need to find a plane. When the plane comes down, am I in the camera? Okay. And when the plane comes down and it swoops down at this bottom position, the pilot will feel himself pressing down very hard against the seat because that is the normal force that he feels, or he feels that he exerts on the seat. So he'll be strapped very tightly on the seat. Okay. So can if the G force is too big, it can crush bones one, okay? Can rupture capillaries. Go watch some science fiction lah, okay? So let me see if there's anything else that I want to talk about. Nothing much, I think. So yeah, so I think this is the end of the topic. Before I go and send you off to do your questions and your task and your assignments, there's a one last demonstration by Miss Ellie, and that will close off the chapter, and I will see you in chapter 8, gravitational field. All right, so take care. Don't stop first. There's something cool for you to see after this. Just let me fade away.
No water. Now I add water. Now.
Ooh, projectile. You can see like this projectile motion when the water came out from the hose. So you can see in one complete circle, as long as the bucket can travel in the circle, water will not fall out unless you slow down the bucket. So go try this at home. Hashtag water bucket challenge instead of the ice bucket challenge. We make our own challenge. Alright, and with this is the end of chapter 7. Miss Ellie and I will see you in the next chapter. Bye-bye.